Hello, everybody. 'Tis I, your fearless leader. So I wrote up the notes today, and I just loaded them into Moodle like less than a minute ago. So they're there for you if you want them. Oh, shoot. I need to update. I'm sorry. I need to update the PowerPoint there because I made some changes to the PowerPoint. Let me just delete that. Put the new one in. So if you one of those people who follows along with the PowerPoint, I have just put the new PowerPoint up there. Yeah. Okay. It's there. Coming. Almost there. Well, anyway, it's at the bottom of the block of material. Okay, so we ready to rock and roll? Let's do it. Lake Isachsen. Lake Isachsen.
It's Isachsen.
Isachsen. Where is Lake Isachsen? I've heard of people having a camp on Lake Isachsen.
I don't know. It'd probably be in Norway or something.
Oh, okay. I thought you were going to say it's in Plattsburgh right now, but it moves. Oh, that's a bad joke. It's okay, though. I get paid anyway. Good jokes, bad jokes, doesn't matter. Where is it? There it is. Okay, so today we're starting chapter 14. 14 follows chapter 13 really closely. 13 was all about cytoskeleton and cytoskeletal elements, and now this is talking about how cytoskeleton is used to make the cell move or make things move inside the cell. Let me pull up my notes to make sure I'm not lying. It's important at all times to have your own personal sound effects. Okay, so we've got two different types of movement. You got movement based on microtubules and movement based on microfilaments. It's two different kinds of microtubule-based movements. And we'll start out talking about those microtubule movements. So that's down. Most of this microtubule stuff was worked out with a model called the squid giant axon. So you know how big a squid is. They're like about like this, right? So they have, you know, they move around using these arms a little bit, but when they're really scared, they take off by contracting this dome, you know, the calamari part of the squid, the part that you eat. It's a big muscular thing and it contracts really fast, squirts water out, and it takes off. So that's what this giant axon is all about. So it's a really big one, easy to get to because you can just cut down this hood or whatever it's called and get into those axons and do a lot of experiments with them. And then when your experiments are over, you can eat them, you know, what the hell. It's good to have an experimental model you can eat. So anyway, that's how this was all worked out. And it was worked out on axons because axons are really long extensions of the plasma membrane. Like you've got some neurons in the base of your spine that go all the way down to your toe. So they're really long, and the cell has to have a way of getting things from the cell body where proteins are made out to the axon, out to the end of axons where proteins are needed. So this microtubules are used as a transport system to get things all the way out to those axons. Hang on a second, I hear my dog whining. It just gets worse if you don't deal with it. Gus, what are you doing? Come on up here. Huh? Sorry about that. Okay, where were we? So we've got two different kinds of microtubule-based movement, cytoplasmic and axonemal. So this is cytoplasmic. We talked about the MTOC in the last chapter and how all the microtubules start here and polymerize away from it. So you've got plus ends away from the center of the cell and minus ends close to the center of the cell. And in chapter 12, when we talk about the endomembrane system, we'll see that, this is like it's either between the rough ER and the Golgi or after the Golgi. It's right in that whole vicinity there. So things are moved around from the rough ER to the Golgi and from the Golgi off to different parts of the cell using this cytoskeletal contraption here. And the directionality of the microtubules, which I was harping on in the last chapter, is really important for this because that gives you a direction. So if you want to send something out to the cell, you would go in the positive direction. You want to bring something back in, they go in the negative direction. So what is moving things are the motor maps or the motor microtubule associated proteins. In the last chapter, we talked about non-motor maps, which help to organize and polymerize the microtubules. These are the ones that are actually motor maps and they're moving things around. So we've got two different kinds, kinesin and dynein. You can see structurally they're pretty different from each other, but they both have like two globular heads sticking out. So this is kinesin, that's dynein there. Big difference, and the thing you need to remember is kinesin moves towards the plus end of the microtubule, and dynein moves towards the minus end of the microtubule. Here's an actual electron micrograph of a vesicle being held onto that microtubule. Okay, where do I go from here? Okay, let's tracks, different parts of the cell. Okay. Okay, so this is the structure. We're on slide 5 now, the structure of kinesin. Later, we'll talk about myosin, and we'll see that myosin is very similar to kinesin in structure. Basically, you've got your two globular heads out here, and these bind ATP and also hydrolyze ATP. And when they hydrolyze ATP, they'll change conformation, and that's what causes the movement. And then you've got this coiled coil structure. Again, like I said, you see this a lot. You've got homodimer here, and they're wrapped together by these tails. And then you've got cargo binding. So this is where the vesicle is going to attach to this carbo loading, cargo binding section. So how does kinesin work? It seems silly, but it kind of just walks along the microtubule as if it had two legs. So here is the sequence of events that needs to occur. So here, this is a cycle, so you can start anywhere in the structure. Let's start here, since this is what they decided to do. So at this stage, before this ATP comes in, you've got a rear leg with ADP attached to it and a front leg with nothing attached to it. And then ATP comes and binds to that front leg, and that causes a conformational change that makes its way all the way up through the structure of the homodimer and affects this globular head over here. So when this globular head senses that this one picked up ATP, it releases from the microtubule, and then it swings forward over here. So that back foot is now the front foot. And once it swings forward, it attaches to the microtubule again. Now the back foot is going to hydrolyze that ATP to ADP, and that causes a conformational change to kind of translate over into the front leg, which then lets go of ADP. Once it's let go of ADP, it can pick up ATP, and that causes the back foot to let go and come forward. And then that causes the rear foot to hydrolyze ATP, and on and on and on. So it just walks down the microtubule one step at a time, always tied to that hydrolysis of ATP, because that's what's providing the energy to make it happen. And let's see. I want to show you a quick video. I showed you part of this the other day, but this, hang on, pause, damn your eyes. Okay, I just got a quick chat. Is there multiple kinesin attached to the vesicle or a single attachment? I think just one molecule is all that's needed to move that vesicle. In this next video, you'll see one molecule of kinesin moving a vesicle, and I think that's the way it works. Let me give you a new share. Okay, so I showed you part of this the other day. Now we can watch the kinesin moving a vesicle here. There he is. You can see it just trudging one foot in front of the other. I keep expecting you to pause for a second, wipe sweat off its brow, and then move on. And here you can see the microtubule organizing center here, and all the microtubules come out from that one place. And there's Mr. Vesicle moving again. These are microfilaments. Here's the mitochondria. I never knew that mitochondria can move, but look at that sucker go. Okay, MTOC, centrosome. And all these vesicles moving along the thing. All right, now we're getting into the nucleus, and that's not what we're talking about today. So
I have a question.
Yes.
So how is it that a structure so small and thin could carry something so large? Is it like that is suspended in substance or something? Or?
Wow, that's a good question. I think when you're at a level that's that tiny, some of the physics that we know don't seem to apply as much, you know? I mean, I'm kind of BSing here, but when you think about an insect, how small they are and they can lift 100 times their own weight or whatever, when you get to a smaller scale, it's different, I think, than the Newtonian physics we think about on the scale that we live at. Yeah, that's a good question. You know, I don't know. This is just an animation. It's not necessarily, you know, to scale and everything. It may be to scale, but it may not be. So in answer to your question, I don't know.
Okay.
Shut up, Dr. Slush. All right, so let's go back to our notes. Okay, so that's kinesin, only used for moving things around in the cell and always going from the minus end to the plus end in the cell of the microtubule. Now, cytoplasmic dynein. So now we've got the other protein, dynein, then is slightly different in structure. You can see you've got these big circular areas and you've got this lever region in the middle, the stalk and the globular heads here. So this is all dynein here. In addition to the dynein, there's this dynactin complex that is also necessary. And the dynactin complex attaches the dynein to the cargo membrane. So there's several proteins involved and we don't know the names of them, and that's okay because that's fewer things to have to memorize. But the dynactin complex then holds the dynein on. And look at this bad boy here. What do we got? We've got a transmembrane protein, band 4.1, spectrin, and and chirin, spectrin, band 4.1, and microfilament here, and then protein of the dynactin complex attaching it. So this is exactly the same structure we saw the other day. Where are we? Come on. Come to me. There it is. Okay, can you see this? I'm showing slide 36 of chapter 13. Do you see that?
No,
No?
still just seeing chapter 14.
Okay, there. So remember this, we talked about this last week. Transmembrane proteins, spectrin and then chirin, and this is what helps to attach the cytoskeleton to the plasma membrane. Well, we look at today's lecture, we see it's the same structure that's attaching dynein to the vesicle. So, which kind of makes sense too, because if this vesicle then eventually fuses to the plasma membrane, you've got this structure that ends up on the inside of the membrane, which is what's there already, and it can connect to everything else. So, it's kind of an important connection between the two chapters there. Okay, so that's cytoplasmic dynein, and oh, I got this here too. So how does this work? When it hydrolyzes ATP, it changes conformation, it lets go, it regrabs, goes back. So it goes back and forth like this, and that little bit of motion then causes it to move down the vesicle, to move the vesicle down the microtubule. So that's your cytoplasmic dynein. Now, axonemoldynein, a tad more complicated. So the axoneme then is the structure that that's inside the cilia. And again, I said this before, but I think cell biologists are getting away from using the term flagellum. Flagellum is just a really long cilia. The structure is exactly the same. The movement's the same. And again, to contrast that from the flagellum in a prokaryote, which is very different in structure. Okay, but anyway, cilia. Here's your cilium, and as you know, cilia are involved in moving things. They do this by this kind of, they're rigid, and they do this power stroke, and then they bend to come back up, and a power stroke and bend to come back up. So it's like putting the oars in and then bringing them back, and putting the oars in and bringing them back. This is used in a number of processes, and I want to show you some, both male and female use of this during reproduction. Let's watch these videos because I think they're pretty cool. All right. Let me do my share thing. Ovulation, ovulation, ovulation. Ovulation. I'm going to skip ahead of ovulation and get to a little bit later.
First 7 days of the cycle, a few follicles begin to grow at the same time. These maturing follicles secrete estrogen hormone into the bloodstream to repair the lining of the uterus for pregnancy. Around day 7, all of the follicles stop growing and begin to degenerate, except for one. This dominant follicle continues to grow and nourish the developing egg inside it. Around day 12, the follicle secretes a large amount of estrogen into the bloodstream. When the estrogen reaches the hypothalamus, the pituitary gland in the brain, the anterior frontal pituitary gland releases a
Just so you know, we can't hear what the video is saying.
You can't hear it?
Around day 14, luteinizing
Better?
hormone
Okay.
causes the follicle to undergo a sudden growth spurt. Right before ovulation, the egg detaches from the inside of the follicle. The bulging follicle releases chemicals, causing one of the two fallopian tubes to move in closer and surround the follicle.
All right, this is where I wanted you to see. This is where the cilia come into play.
The follicle swells until it bursts open, ejecting the egg and fluid from the follicle into the abdominal cavity. In response, the fimbriae, tiny projections at the end of the fallopian tube, sweep across the ovulation site and pick up the egg. Microscopic cilia on
Cilia.
The egg's surface transport the egg to the entrance of the fallopian tube. Inside the walls of the fallopian tube, muscular contractions gently push the egg towards the uterus.
All right, so now it's saying muscular contractions, but there's this other video looking at it from the sperm angle that says it's not muscular contractions, it is cilia at that point too. So let's watch Mr. Sperm, see what he has to say.
The sperm must pass through the cervix, opening into the uterus. Usually it remains tightly closed, but here the cervix is open for a few days while the woman ovulates. The sperm swept through the cervical mucus, which is thinned to a more watery consistency for easier passage. Once inside the cervix, the sperm continues swimming toward the uterus.
So here you've got flagella moving the sperm.
Millions will die trying to make it through the mucus.
Poor
Some
bastards.
sperm remain behind, caught in the folds of the cervix, but they may later continue the journey as a backup to the first group. Inside the uterus, muscular uterine contractions assist the sperm in their journey toward the egg. However, resident cells in the immune system mistaking the sperm for foreign invaders, destroying thousands more.
Sorry, buddy.
While the other half swim toward the tube containing the unfertilized egg. Now, only a few thousand remain. Inside the fallopian tube,
Ah.
tiny cells push
There's your cilia, and they're moving the egg.
the egg toward the uterus. To
Push-
continue, the sperm must surge against this motion to reach the egg.
They're pushing a
Some
fluid.
sperm get trapped in the cilia and die. During this part of the journey, chemicals in the reproductive tract cause the membranes covering the heads of the sperm to change. As a result, the sperm become hyperactive, swimming harder and faster toward their destination. At long last, the sperm reach the egg. Only a few dozen of the original 300 million sperm remain. The egg is covered with a layer of cells called the corona radiata. The sperm must push through this layer to reach the outer layer of the egg, the zona pellucida. When sperm reach the zona pellucida, they attach to specialized sperm receptors on the surface, which triggers their acrosomes to release digestive enzymes, enabling the sperm to burrow into the layer.
Sorry.
Inside the zona pellucida is a narrow, fluid-filled space just outside the egg cell membrane. The first sperm to make contact will fertilize the egg. After a perilous journey and against incredible odds, a single sperm attaches to the egg cell membrane. Within a few minutes, their outer membranes fuse, and the egg pulls the sperm inside. This event causes changes in the egg membrane that prevent other sperm from attaching to it. Next, the egg releases chemicals that push other sperm away from the egg and create an impenetrable fertilization membrane. As the reaction spreads outward, the zona pellucida hardens, trapping any sperm unlucky enough to be caught inside. Outside the egg, sperm are no longer able to attach to the zona pellucida. Meanwhile, inside the egg, the tightly packed male genetic material spreads out. A new membrane forms around the genetic material, creating the male nucleus.
Okay, here come microtubules again. We're going to see that happen here.
The genetic material reforms into 23 chromosomes. The female
There's your mitotic spindle, which is chapter 24. But your centrosome and microtubules coming off of it. Told ya.
The two sets of chromosomes join together, completing the process of fertilization. At this point, a unique genetic code arises, instantly determining gender, hair color, eye color.
Okay, so two things there. One, it killed some good class time. And two, you could see both the axonemal and the cytoplasmic microtubules in this. The axonemal in the cilia, moving the fluid over the surface, moving that egg, and in the flagellum of the sperm, moving the sperm. And then you can see the cytoplasmic ones here being involved in the mitosis after the egg cell is fertilized.
So the cilia aren't actually physically moving the egg, they're just more creating a current of the fluid that moves the egg in turn, right?
Right, exactly.
Okay.
And the cilia do a similar thing in your lungs where, you know, your lungs are always putting out, your bronchial passages and everything are putting out like a thin watery mucus, and the cilia are doing the same thing. They're beating up and bringing that mucus up out of your lungs, out of your bronchi, into the back of your throat and down to your stomach. So again, you know, you're inhaling all kinds of viruses, and some of them will get caught in that mucus and get, you know, cleared out of your lungs by that cilial action. Okay, so that's mainly in our bodies what cilia do. They move a fluid over a surface like that. Okay, what's next? Ooh, so here's the structure of the axoneme. Pretty complicated structure. I mean, compared to the cytoplasmic microtubules. So you've got a central pair of microtubules. So these are just single microtubules that are connected through these proteins in the center. And then on the outside, you've got 9 doublet microtubules. Of each of these doublet microtubules, you've got a complete circle for one and a partial circle for the other. I think there's 13 protofilaments in this one and 11 in this one. So the complete one is the A tubule, the partial one is the B tubule. And then you've got cytoplasmic dynein, or not cytoplasmic, I'm sorry, axonemal dynein, and that is attached to the A tubule and is going to reach across and grab the B tubule. So this dynein is going to grab that microtubule and walk along it. So just like we saw kinesin walking earlier. And when it does, basically it's grabbing this and moving it, and it moves down while this one moves up. So the 2 microtubules are going to slide with respect to each other and let go and slide and let go and slide. So that's what the movement does. But Dr. Slish, that's not the way the cilia move. They move back and forth. Correct. Good question. So in addition to that dynein that's sliding the microtubules with respect to each other, you've got these interdoublet links called nexin, the red thing that's behind the dynein. And you also have these radial spokes. So the radial spokes are kind of keeping the microtubules out, holding the structure. And these nexin links are converting that sliding motion into a bending motion. So you can imagine if you attach these 2 together and they do this, this one has to bend to stay with that one. So, and it goes back the other way. So that's what that nexin, interdoublet nexin link is doing. It's converting the sliding motion of this into the bending motion that allows the microtubule to move. Okay. Comments? Discussion points? What are the ethical ramifications of this? Nothing. We don't do ethics in this class. Nothing. Okay. So that's it for microtubule-based movement. Pretty simple. You know, you've got moving things around inside the cell, moving vesicles around in the cell, and then you've got axonemal movement. More complicated is your microfilament-based movement. So microfilaments, being made of actin, are going to move based on their interaction with myosin. Myosin, there are way too many myosin genes in our genome. I have no idea why there's this many genes, but there's 15 families of genes. So each family has probably got 10 genes in it. So there's like 150 myosin genes in our genome. I think, in my opinion, that's too many, but who cares what I think? So you've got a number of different structures that can be used in different things. Some are just used structurally. Again, let's go back to chapter 13. There it is. Okay, do you remember this? Let's zoom in here. Myosin, I guess it's not in the figure. No, but myosin is these blue things that are attaching this. So myosin and calmodulin are involved in structure here in the microvillus. So it can be structural. So I imagine these shorter ones are more important in structural ways. So this is the one that I'm most interested in because I'm a muscle guy from way back. And with your average, your skeletal muscle and cardiac muscle, the myosin is myosin 2. So myosin 2 is again a homodimer coiled coil structure. You've got a globular head, and the globular head has got an actin binding region, and also ATP binding and ATP hydrolysis. So this is the business end here. This will bind ATP and also bind to the actin microfilament. Then you've got a hinge region here where it's got some flexibility, and that's what helps it to move when it starts to move. And then you've got structure here with these coiled coil tails. These tails then can interact with other myosin tails. You can see that here in the thick filament of skeletal muscle. You know, the thick filament itself, it's all bundles of those tails attached to each other. And then you've got the hinge region here and the head sticking up and reaching across to the thin filament. Also, when we talked about stress fibers and cell crawling, you've got myosin tails interacting with each other in an anti-parallel way. And that then cross-links two different stress fibers. And when the myosin walks along the stress fibers, it pulls them together and you get shortening of the cell. So we've got structural tail, the hinge region, the head where all the activity is. And then here you've got the myosin light chains. Myosin light chains are really important in smooth muscle when we see smooth muscle contraction later in this chapter. Very important for that. Skeletal muscle, I think they're also involved in regulating the myosin heads as well. But basically, your myosin light chains are regulating the ATPase activity of the myosin head. So they're important as well. Okay. And I think that's all that I prepared for today. Normally that would take me an hour and 15 minutes to do, but with the way things are here in these Zoom things, it goes a lot faster, right? Because all the notes are there. I'm not writing it on the board. So sorry, it's a little bit short today. Any questions about this? Any comments?
How does cilia move? Are they like, do they just move naturally, or do they move like because of the fluid that they're in, or is it like a signal that they're receiving from somewhere? How do they do that?
So if it's in the, I'm not 100% sure, but if we're talking about respiratory tract or the fallopian tubes, I think they're just constantly signaled to move. So they're always doing this. Okay. If you're talking about cilia in a paramecium, right, single-celled organism, then it has to do with electrical activity in the plasma membrane. Remember, they're all covered with the plasma membrane. And when they depolarize, it allows calcium in, and calcium activates that movement. So, and you can imagine for a single cell, you'd have to be able to control it. Otherwise, they'd just be going straight all the time and they'd be screwed. So this allows them to turn and back up and everything because they are regulated. But I think in multicellular organisms, Again, I'm kind of making this up, but I think they just keep moving.
So it's not like so it just comes naturally, or
It, I would call it constitutive. Yeah, that's natural, I guess, but just constant motion.
okay.
I could be wrong though. I mean, there could be an electrical signal too that's just signaling to go, but you know,
Very nice. Thank you.
I'm rarely wrong though. Don't bet against me.
Okay. Noted.
Anybody else?
I have a question. You might have to go back to the slideshow. It's on slide number 6, where you were telling us, I think about the kinesin, and it was step 2 on slide 6. It was that when the back foot senses the ATP has bound to the front foot. Did you say, so up on step 2, is it lifts up, does it dump the ADP at that point?
Hang on a second. Oops, get out of my way. Okay, so we're right here.
Yeah.
Okay, so ATP is bound to the front foot, and now the conformational change kind of translates through the molecule to here, and that causes this to let go. Now it's hanging on to its ADP, but it's let go here, and it swings forward to there.
Got it.
And then it lets go.
Okay, great.
Okay. Okay, any other questions, comments? Christy Trask is in this class. I haven't seen you in my class in a while. I've missed you, Christy. Where is she? There she is. We'll have to talk again later about your career path. Okay. Any other questions or comments? Anything going on? No? All right, again, sorry it's a little bit short, but this is typically the amount of material I cover in this class. So I hate to push it too fast or too hard. So, all right, we'll call it a day, and have a great rest of your week. I'll see you on Thursday.
Thank you. Have a good day too. See you Thursday.
Okay.